the last topic that I wanted to broach today is another that you've done a lot of work on and that's come up in the conversation a few times already. And I guess it's two things. It's dark energy and dark matter. And maybe we should first just explain what they are, how, and if they're related before we get into the relationship to fine-tuning.
Okay. So dark matter is the dominant mass that we have in the universe. So we've actually known for almost 100 years that there has to be mass out there that we can't see. But it was really the coming of the 1970s where people realized that this unseen matter has to be dominant. And what I mean by dominant is that there are often at least 10 times as much dark matter in a location as there is visible matter that you can see in terms of stars and starlight and all that kind of stuff. And dark matter can't be something like atoms because atoms interact with light. And the whole point with dark matter is light is just travels through it. It's transparent. So that's been known, said for almost 50 years now that definitely there's a lot of dark matter out there. What we have uncovered in the last 25 years, of course, is that that's not the only dark component in the universe. So people looking into the distant universe, looking at these exploding stars called supernova, they were trying to measure the rate of expansion of the universe, and they expected that rate to be slowing down. So, a universe is born, it's expanding, and they expect that expansion to be slowing. But what they found is instead of slowing, the distant universe appears to be speeding up. Right? So the conclusion from that is that if we look at Einstein's cosmological equations, we need to put a term in there to give us this accelerated expansion. And the only term that we can add that can do that is this stuff we call dark energy, right? So it's not like matter. It's a very different kind of energy. And it accounts for 70% of the energy density in the universe. So it's the dominant energy that's there. It's very spread out. It looks like it's uniform. So, there's some here inside my hand, but the gas in the room dominates it in terms of how much energy is inside my hands. But dark energy is everywhere. Now, the question about whether or not they're related, we don't know. People think that dark matter is potentially a particle that we haven't yet discovered as part of the standard model of particle physics. Dark energy, well, there doesn't seem to be a natural place for dark energy in any of our physical theories. We really don't understand what dark energy could be, right? There's lots of ideas, lots of suggestions for fields and all this kind of stuff, but nothing robust. Nobody's come away and say, we've nailed what dark energy is.
I think that I have wrapped my mind around the idea of dark energy being everywhere, but the way that dark matter is typically portrayed, it's seen sort of around the edge of a galaxy in a sort of halo. And
yeah, so that's a terrible name. That's the problem. So the picture, the word halo makes you think that it surrounds, but that's not the truth. So dark matter actually is concentrated in the middle of the galaxy and drops off towards the edge and then continues outside. So it goes out into a region of the galaxy we call the halo because it surrounds the galaxy we can see. But dark matter actually feeds all the way into the center of the galaxy.
Okay, that answers one question for me and raises another. So the question that it answers for me is I had been confused about why dark matter would help through gravity keep the galaxy together when in like a model like the solar system, it's the star at the center that keeps the planets from flying out. So if it were outside, I wouldn't have understood as well, but this makes more sense. But then the question that it raises for me is that I thought that one of the major problems, granted that I believed that dark matter was outside of galaxies, one of the major problems we had in or have in determining what it is that it is so distant. But based on what you've just told me, if it is everywhere and it's concentrated also in the middle of the galaxy, then we should be able to find it in something like the in a particle accelerator or terrestrially in some. Is that accurate? We don't have to be looking for it through telescopes?
No. So yeah, if you do that, you've probably got like 10 dark matter particles in there.
Oh, okay.
Right? So they're here, right? So yeah, there are definitely experiments that people are trying to do here on Earth. So number one is, of course, the Large Hadron Collider. They're looking to smash things together to produce a dark matter particle. And everyone wants to do that because that would be Nobel Prize winning stuff. So that gets people excited. But there are other people trying to do direct detections. So there are a whole bunch of experiments. There's one called Dharma Libra, which is in Italy. It's in the Gran Sasso road tunnel. There's a laboratory there. It's basically a giant crystal of salt, and it's very pure. And what they are doing is that they've got that sitting there, and they've got dark matter particles coming through, and they're hoping that every so often a dark matter particle will strike one of the atoms and kick out an electron and produce a little flash of light. And of course, they already see little flashes because radioactivity and cosmic rays already produce a signal. So Dharma Libra has actually found this sort of modulated signal that seems to go up and down on a yearly basis. And they suggest that is due to, so here's the sun and here's the Earth's orbit. So the sun travels this way, like so. Let's try that again. And so if you can think about it, for part of its orbit, the Earth is going into the dark matter, and part of the orbit means it's coming away. So if you've got it's like being in the rain, running into the direction of the rain and running away from the direction of the rain, you get different levels of wetness, right? So what they're suggesting is that this modulation is due to the Earth's orbit going through like the dark matter of the Milky Way. The problem is that only they've seen it, and there are other experiments looking for it, and they haven't found it. But in Australia at the moment, there's a gold mine in a town called Stawell, and they're building the Sabre laboratory, and they're building a not identical but very similar experiment, big chunk of salt, and they're going to look for that signal here as well. And the reason that you want it in the southern hemisphere is that some of the variation that you get might be seasonal, right? They're in a road tunnel, so even the flow of traffic through the tunnel changes through the year and might be imprinted on the signal. If you pop it in the southern hemisphere, of course, our seasons are 6 months out of phase. So if we see the same peaks and troughs in the southern hemisphere, then that suggests it's an external signal. If we see them out of phase, it suggests that they're picking up something to do with the seasons on Earth. So yeah, people are trying to do direct detection of dark matter.
Well, this is terrific because my understanding of dark matter has just totally shifted. I had not realized that there were 10 particles in my hand. I thought they were all very distant. So, okay, that's awesome. And then the last thing, though, to finish up with here is, where do dark matter and dark energy fit into fine-tuning?
Well, so they fit in quite a bit, but the fact that we know so little about them makes them even harder to understand. So dark matter dominates the universe, and we don't know quite when dark matter was formed. It was probably formed after inflation, so therefore it's somehow tied to the standard model of particle physics. But the problem that we have is that there's dark matter dominates, which means that after the Big Bang, it's dark matter that collapses and pulls the gas along for the ride, which produces galaxies and stars. Now, if we had significantly less dark matter, then that scaffolding in which we form galaxies and stars, that disappears, right? So that would cause real problems in that it would take a lot more effort for the universe to form galaxies and stars, which we need for life. If we have a lot more dark matter, then that gets things to clump a lot faster and pulls gas in, and it very rapidly can turn gas into black holes, right? You can run through the entire sequence of forming stars, etc., massive stars, they explode, etc., and then make black holes. So you can run through the entire sort of sequence we need to form heavy elements very, very quickly, and maybe there's not enough time there for life to form. Dark energy, though, is a much more dangerous thing for life in the universe. So if we had no dark energy, then everything would have been basically the same. But if we had, say, 10 times as much dark energy as we do now, that would mean that the epoch of acceleration would have started 10 times earlier in the universe. So instead of occurring 5 billion years ago, it might have been 500 million years after the Big Bang. So if you imagine that dark energy accelerated expansion kicks in, so the Big Bang is formed, hydrogen and helium, and it's all galaxies starting to clump together, but then the universe starts to accelerate. Then all of that stuff that was falling together gets pulled apart again. So you end up, if you have too much dark energy, you turn the universe into a thin soup of material very, very early on. And again, if you do that, no galaxies, no stars, no planets, no people, right? So you shut off that entire route. Now, again, exactly how much dark energy you need to do that is, it's a kind of complicated thing, because even if you have a little bit of extra dark energy, you still form galaxies, but you form them very compact because you get this rapid clumping. And small galaxies are not good places for life because there's just too much going on. So it's probably a complicated relationship, but you wind up dark energy by more than a few, then that's detrimental to life. Now, again, we don't know what the range of potential dark energy densities in the universe could be, right? So minimum is probably 0. The maximum, some people suggest that that's around 10 to 120 times as large as the dark energy we see today. So if you imagine that you had a dice with 10 to the 120 sides to it, and you roll it, the chances of it coming up 1, which is what we need for our universe today, is small. Chance of it coming up 10, which is a bit dodgy for our universe, it's more likely to come up with a number, let's say 10 to the 56, and that means no chances of life whatsoever. So again, why we've got dark energy in our universe and why it's comparatively so small that it's allowed roughly 10 billion years of nice-ish evolution for the stars so we can be here, but in the future it's going to shut down everything as the expansion accelerates. Why it started off so small is a big question.